Deep neural networks are linearly connected via weights and biases, as you see over there in these diagrams. It is noted that only a solution of a simple linear regression model can be obtained if activation functions are not implemented. The activation function should be implemented in ANN in order to represent a complex non-linearity such as those that exist in most engineering problems and also in neurobiological systems of our brain. In our brains, outgoing signals are activated by neurons when the combined input stimuli to the neurons build to a threshold value. So our brain is capable of cope with a nonlinear response against the external conditions, weathers and psychological conditions, and any of the conditions can make our brain to think in nonlinear fashions. Therefore, in deep learning networks, artificial neural networks, the weighted sum of previous input signals is into the activation functions, which play a role similar to the stimuli of the neural biological systems of our brain. And here, the weighted sum of biases, which is a tentative neuron value shown in circle, is based on linear relationships because all these neural networks are constructed based on combination of bunch of linear relationships, and we have to use and filter those neural values, I would say they are temporary neural values, into the activation function to come up with a final neural values which can cope with a non-linear behaviors and complex non-linearities that we can find for our engineering problems and science problems and even social problems. Similar to neurobiological systems of our brain which can cope with a nonlinear behaviors, the activation function also in neural networks, artificial neural networks, can cope with a nonlinear relationship between inputs and outputs, and we have to reflect those relationships in our engineering problems. This figure represents a typical linear and nonlinear relationships. We have to shift from linear behavior to non-linear behavior of our neural networks, artificial neural networks. As you see, but the x-axis represents the tentative neural values. I call it tentative because the neural values without activation function is not the final neural values that we need to obtain. So that the final neural values obtain the y-axis by using activation function, by applying activation functions in order to cope with the nonlinear behavior of our engineering problems. And here you see the activation function inside of circle neurons to come up with the final neural values, and I'll explain it soon, but if you understand that's the indicates a sigmoid activation function inside of the neurons, which means that all your tentative neuron values is going through and pass through the activation function and in general, and sigmoid in particular in this neural networks, so that the neural networks are now becoming a final neural values. We have a typical activation functions, tanh, sigmoid, and the relu and liquirelus. And if you see over there, the functions is experiencing nonlinear curve here and here. the x-axis, 4x-axis, which is significantly larger than 1 or 2, both in positive regions here and negative regions there. You see the nonlinear behavior of the curve where your slope gradually becomes 0. Slope becomes 0 here at these regions for both tanh and sigmoid, where your maximum and minimum for tanh is 1, between 1 and -1, whereas your maximum and minimum for sigmoid goes like 1 and 0. Everything else are exactly similar except those extreme values that represented by those two activation functions, and of course their formulas are different, so therefore each given input values you will come up with a different tanh value and sigmoid value, but they are not that different. They are similar values but different expressions. So the x-axis, as I said, x-axis represent a tentative neural values here, and the same thing here, and whereas y-axis indicates a say final neural values. This is what happened in the circle. If you see the circle, there's a indication of a activation function, which means that your temporally tentative neural values are passing through the activation function to come up with the final neural values. And what do you mean by the passing through the activation function? I mean by that is you put tentative neural values in here if you use a sigmoid, and in here if you use a tanh. That's simple concepts. And there's another two famous activation function that is being used recently, and that's ReLU and LiquidReLU. ReLU is a straight line for positive input regions, and there are vanishes for negative input regions, whereas you have a little slope and negative regions for LiquidReLU. Because when you do, what happens is that if you gradient or slope goes 0 right there, you will have some problems with the training, especially for the process of backpropagation. I will share that information with you in next lecture. Okay, so when your slope and gradient becomes 0 or vanishes for larger input regions, and here we have some problems. The gradient of tanh or sigmoid right there, activation function becomes small or even close to 0 right there when inputs have a large absolute value, very large negative or very small positive value here and here, here and here. Okay, for example, here and here, here and here, and here and here, for both very large positive value, very small positive, very large positive value, very small positive value, and hence small gradient substantially affects a backpropagation, which is commonly implemented in ANN in devising weights and bias. So your gradient becoming vanishing for these regions, for very large positive, for very small positive. This is a problem. So that the if that happens, this will hinder backpropagation, lowering a training accuracy of ANNs, so that the ANN will be clocked and unable to exit loops of backpropagation algorithm, so that the small gradient are leading to weights and biases that cannot be updated efficiently during backpropagations. If that happens again, the computational resources will be wasted with the weak training results when vanishing loops are encountered. So, but we can fix this problem by properly initializing data sets before backpropagation begins. But I'll also explain that later. There's a lot of initialization techniques are proposed, and we'll take a look at that later as well. So here you're watching a gradients here. Gradients becomes very small in this region, and in this region, especially for sigmoid, for very large positive and very large negative, positive right there. Okay, so this will just waste your computational resources, and vanishing loops is very bad because you are encroached and unable to exit loops of backpropagation algorithm, which makes your training bad, also making your weights and biases, they cannot be updated efficiently. Okay, and again, you know, this x-axis represent a tentative neural values, and once you go through the activation function, then y-axis represents a final neural values. And that's the reason that we have a ReLU more popular these days, because ReLU do not show vanishing problems for positive input regions over there, because there's the linear relationships is presented, so that the vanishing problem is not a problem anymore in this region. But still we have some problems in negative zones where the gradients does not exist, so that we have some vanishing problems encountered in here, which makes your backpropagation algorithms difficult. So in order to fix that problem, ReLU has been proposed by providing a little slope in negative zone right there, so that you can still have some rooms to make your backpropagation algorithm going okay without being crocked and oscillated within the loops of backpropagation algorithm. So this is why currently the ReLU and ReLU is more popular than the tanh and sigmoid that has been popular before, because of this reason. Okay, this comparison is proposed by this reference, can be found from the book of that I'll be publishing with Elsevier, the topic of AI-based reinforced concrete design soon. And all these numbering systems and sentences and figures and tables are from the book that I'll be publishing with Elsevier, and you'll probably find all these references from that book as well. And if you see the training rate is converging to a very small number, that means you're going to have a weights and bias is being calculated. But if you take a look at these two diagrams in comparison of them, the ReLU converges fast than the curve calculated by the tanh, and they are very significantly efficient than tanh calculated curve. And this is epoch, these iterations that you need to perform for trainings. And training is just simply a process that you want to calculate weights and biases by matching inputs to output, or by fitting inputs to output, or by predicting output from the inputs. And fitting, matching, mapping, prediction, they are all same lingo to explain the training process. It's actually a training process. It has two steps. The first one for the calculations of ANNs, and we have studied how the ANN is carrying out its calculations. I mean, between layers. between layers, circle to circle, right? And that's a forward calculations. And after the forward calculation of a and n is done, we calculate the error function, which means that the difference between the calculated, the values based on forward network, and the observed test data, and that's, we call that error functions and or cost functions. All those functions should be minimized so that your weights and biases converge to true values. And when you do that, you're going backwards to the first layer. It is called a back propagations. Back propagations, and okay, back propagation. Back propagation, and after going through the back propagation, you do the forward calculation of a and n one more time to see if your weights and biases are revised, or if that's revised, and how much revised. And that one cycle is called epoch. And probably in my experience, you need probably going through like 30 to 40,000 epochs for simple reinforced concrete beam design, and some of them will probably go over 50,000 epochs, and that's very lengthy process. You need to repeat a forward calculation of a and n's and backwards propagations. One iteration, you revise your weight and bias once, and probably you have to repeat that 40,000 times and 30,000 times to see the corrected final revised weights and biases.